Hello, everyone. Welcome to the Asiagraphics webinar, session 10. So my name is Tuanfeng Wang. I'm a research scientist from Adobe Research. So today we have two great speakers, Professor Ariel Shamir. He will talk about non-photorealistic vision and graphics, and Professor Lingjie Liu. She will talk about neural representation and the rendering of 3D real-world scenes. So for the first talk, Professor Ariel Shamir is the former dean of FVRZ School of Computer Science at Richmond University in Israel. He received his PhD in computer science in 2000 from the Hebrew University in Jerusalem and spent 2 years as a postdoc at the University of Texas in Austin. Professor Shamir has numerous publications and a number of patents, and was named one of the most highly cited researchers on the Thomson Reuters list in 2015. He has a broad commercial experience consulting various companies, including Disney Research, Mitsubishi Electric, PrimeSense, Verisk, Dongdi, and more. Professor Shamir specialized in computer graphics, image processing, and machine learning. He is a member of the ACM SIGGRAPH, IEEE Computer, Asiagraphics, and Eurographics associations. So without further ado, let's welcome Professor Ariel Shamir.
So today I'm going to talk about non-photorealistic vision and graphics, which is funny because Lingjie is going to tell you how to capture reality. But so maybe these are the two sides. But in general, I'm going to cover a few papers that you can see listed here. And this is a joint work, obviously, of many people, both here in Israel, in the US, and in China and other places. The works are going to cover both analysis and synthesis applications. If you want to learn more or see more details, I'm going to put here my website URL so you can then later visit it if you want. So first of all, let me explain what I mean by non-photorealistic, right? So basically, this is everything that is not captured. So you don't use cameras, or what you do is you either draw it manually or render it using some computer algorithms. And some examples that you're going to see are animations, paintings, and also sketches. So this is what I call non-photorealistic content. And one of the key questions that I'm trying to ask and also do in various works is to see how well the algorithms that we all know so well work on these types of contents. So, computer vision, as I wrote in the abstract, advanced significantly in the last 2 years. And some examples of the algorithms or tasks that it can do is detection of specific items or people, segmentation of parts of an image, and also tracking over time in video, for example. The question is how well these algorithms work on non-photorealistic input. And obviously, most of these algorithms are working with neural networks, and this is sort of the key technology today to use to solve these different problems. So here's one example. This is ByTrack from last year's paper. Amazing work that, as you can see, can track people, numerous people in one frame in real time, without much trouble. So this is amazing work when you think about photorealistic content. But then when you move to non-photorealistic content, for example, in this movie, you can see that maybe the people are tracked well because they look like humans, but then you have also characters that are, tractors or cars or objects that are animated. And obviously this can't be tracked using this algorithm. But also in other types of animations, in this example, you can see human or humanoid characters. And we're trying to run the same algorithms that I've shown you before. And unfortunately, as you can see, none of the characters were captured. They were not even detected using these algorithms. And the key question is what makes really the difference? Now, other tasks such as semantic segmentation of images, again, work well on photorealistic images, as you can see here. We can segment the pixels of each image to different classes, such as dog, horses, cows, people, and so on. And current algorithms work very well on photorealistic images. They tend to gain almost 80 or 90% precision. But when you move to other domains, such as art paintings, you see a very big drop in performance. Lastly, another example that I'm going to discuss is facial landmark detection. This is something that almost everyone has or in his or her phone today. So tracking the landmarks of a face is something that was well researched and works very well. But again, when you move to non-photorealistic domains, you see that it is totally inaccurate and many times not really useful. So what actually makes the difference between these two domains? The first is that the appearance itself is very different in photorealistic and in non-photorealistic images. The textures, the colors, they're always different. The second is that there's a very large variation in style when you talk about non-photorealistic images. You have 2D renderings, you have manga, you have cutouts, stop motion animation. All these domains, although I gathered them together to be non-photorealistic, each one contains their own characteristics, and I'm not sure we can think about all of them together as one domain. The third is that there are many non-humanoid characters in these types of animations and movies. And again, most of the algorithms today in vision, they assume that what you want to track or what a character is a human, or at least a humanoid. So this also makes it very difficult. And lastly, even if you have a humanoid character, a single character can often change shape and color even in the same scene. So here's an example of one character, and as you can see, he can change abruptly from one shape to another, and all these different manifestations of the same character must be, in a sense, clustered or detected as one character. And this is extremely difficult for machine vision today. So in essence, all these things tell us that the non-photorealistic domain is really a very different domain than images and pictures that you take from your camera, and therefore it needs a different way of handling. So one way that people have used or tried to refine algorithms from one domain to another is just use some base pre-trained network and then refine it using maybe a smaller database that will signify better the domain that you're working on. But unfortunately, in animations and in art, there are almost no data sets that you can use for refinement. So certainly not for tracking, not for segmentation, not for point detection. So that's a serious problem. The last thing is that each animation and artistic style is different, as I've shown you before. So even if you train a network for a specific style, it might not work for other types of style. So the approach I'm going to show today for various tasks is really how do we use unsupervised or self-supervision methods as much as possible to learn and to map to better representation. So the key point here is really to learn a new representation that will be able to solve these problems in this very different domain of non-photorealistic images. So let's start with the detection problem. In this case, we were trying to learn what we call a style-aware representation for animation. And when we talk about style-aware, we mean a specific, let's say, series or a specific animation style. we start by taking an existing footage of a video and then segmenting it to shots. Then we use some proposal detection algorithm, which is a base proposal detection. I'm going to talk about it in a minute. And then we use tracking on those proposal detections. Later on, we use these tracking algorithm in order to create a fine-tuned network that will learn the semantic embedding for this specific style of animation. And then once we have this specific embedding, we can run algorithms that are much better and have much better precision and recall than the usual ones. So let me go a little bit into the details how we do this. First of all, shot segmentation, we were using usual methods like color histogram changes. The proposal detector was refined and fine-tuned not just to look at the human, but also to try to detect other types of objects or animals, but again, not fine-tuned for specific style, but in general for animation. And it was oriented to create high recall instead of high precision, because later on we're going to filter everything to create a specific style representation. And lastly, we were using multi-object tracking, which is a graph-based tracking algorithm. Now, all these can be used on any animation style, but the real difference is really the constructive fine-tuning of the network. So after we do this and use general algorithms for these steps, what we use is contrastive fine-tuning of a mapping network in order to map the representation of this specific series. So what is contrastive-based learning? We train an embedding network based on what we call triplet contrastive learning. And this is something that people have been using for a long time. And the idea is that you have an anchor candidate of a character. And then you must look for two others. One would be a positive example, meaning that these two must be the same, must have the same representations, because basically they are from the same character. And then you're going to have a negative example of a different character. And then what you do in the mapping, what you want is to map these three different points in the representation space so that the positive ones would be closer than the negative one. And what you use is basically the difference between the distances. So the distance between the anchor and the positive must be smaller than the distance between the positive and the negative, plus some margin, which we call alpha here. And now you do this not for a single one, but you sum up over many triplet examples, and that helps you refine the mapping network so that it will achieve a better representation for your specific style of animation. Now, how do we find these triplets? So here comes our main hypothesis. We say that if we have in the same frame two different characters or two different candidates for character, these would be the anchor and the negative example. And then since we are using tracking, then we search for the same anchor in a different frame, and then we use that as the positive example. And now, since we were tracking many candidate examples, we have many such triplets, and we take them all together and we train a network using this. And again, remember that this is all done in an unsupervised manner, right? So we don't really need the human in the loop in this or any other type of labeling. So here are some examples. You have some regular triplets. You have the anchor and the positive example, which is very similar, but probably with a different pose. And then you have a negative example, which was in the same frame as the anchor, but it was a different character. But also we have many times something which are more interesting triplets, such as the example I've shown. The same character might change shape or size or color, but because we are tracking it over time, we are still using them as positive examples and then comparing it to negative examples. Unfortunately, because this is an unsupervised method, there are also some false detections. So for example, here the anchor and the positive example, although they look similar, they are different. And you have also the some non-characters at all that are appearing. But since we have many, many such triplets, we can refine the network correctly and map it and create a better representation. So here you see examples of the representation before we did the self-supervision or after we did the self-supervision. These are 3 characters from an animation sequence. And as you can see, using t-SNE mapping, the candidates are clustered much better after you do the self-supervision and you refine it for this specific animation sequence. So the first application we are using this for is really, as we called it, cast or dictionary building. So once we have a video in an unsupervised manner, we can find all the characters that appear in this movie, right? Now, how do we do that? So we, first of all, train the mapping network, and then we map all the candidates to some, semantic domain. In this domain, we cluster all the candidate boxes, as I've shown you before. And then we filter all the insignificant clusters, and the large clusters, we assign one character or one representative for each cluster. And this allows us to find all the characters that appear in this movie. So here's an example of the Cars movie. And I want you to notice, first of all, that we managed to find different characters, although their appearance is very similar. So all these cars are actually different characters in the movie, and they are in a different cluster. So we managed to find them and create a different character for each one. Unfortunately, there are some mistakes. So here's an example of the same character, although they appear in different clusters. So we have 2 characters in this case. And also sometimes we also have just false representations. In this case, this is the South Park series, and this is again one of the chapters, and we can again found all the different characters in the movie. You can see all the main characters, but what's interesting here is that you can also see what is called the long tail characters. So these characters appear only maybe a small amount, or maybe in only one chapter of the series, and still our algorithms could detect them and find them in the movie. And again, as I said, there are some non-characters and some errors in the algorithms still. We did some comparison to previous work and managed obviously to on all measures to get better representation, really almost 90% in precision and in recall as well of all the characters in the movie. Now, once you have all those characters and you have the clusters of examples, what you could do is then you can name those clusters or name the characters, and then you can use all the candidates for a training set of a classifier. So basically, the user only needs to name the character that we found in the dictionary, and then automatically we can build a training set and use a multi-class classifier to classify all the different characters in the movie. So again, we were trying it on various different animation styles, and we got very good results, almost above 90% precision most of the time, and high recall as well. Lastly, we can use this type of algorithm to track different characters over all the movie, because we can also detect them throughout every frame. Now, notice this tracking algorithm actually doesn't use any tracking and no temporal coherency. We only detected the characters separately in each frame, and still it gives us very good results for tracking non-humanoid characters as well as humanoid characters. And in the future, obviously, we can incorporate this also in a tracking algorithm. Okay, so let's move to a little bit more distance domain. And in this case, art. So not animation, but real artistic images or artistic paintings. Now, if you can see in this example, there's a huge difference in many aspects between photorealistic images and artistic images, even if they are realistic images. Now, what are these differences? So as I said before, there are a lot of color and texture differences between artistic paintings and real photographs. There's also a lot of content differences, right? So artistic paintings tend to convey specific images or specific themes that many times are not really realistic. And lastly, there's also some geometric differences. And in art, certainly, you know, the shape of both humans, animals, and even, you know, scenes are always can be distorted severely. So all these create challenges again for computer vision algorithms. And as I've shown you before, if you try to run the state-of-the-art segmentation algorithms, you find that the performance drops rapidly to around 30 or 40%. So we were trying to tackle exactly this problem by segmentation in art. And now, of course, there are many works today that use neural network for art, and most of them are generative in a sense. So all of you, you know, probably heard about StyleGAN and DALL-E that create, you know, amazing pictures and photographs. There is also a lot of work on style transfer, where you can take a photograph and convert it to a specific style based on some images. But unfortunately, when you look at perceptual tasks like segmentation or detection or algorithms, there's no real you know, work up till today. So we were trying to tackle exactly this problem of segmenting artistic images. And the technique we were using, again, because of the large domain gap, was domain adaptation. And previous work also used domain adaptation, and they used mainly two tasks or two techniques. One of them is called augmentation or image level augmentation, where you take some labeled data, for example, segmentation data of photographs, and then try to change it to look more like the specific domain that you're looking at. And the second was what we call feature level domain confusion. So I'll describe two of those that you know, we were using on a data set that we created that we called DRAM data set, which is diverse realism in art movements. Specifically because we need some data in order to test our algorithms and also in order to train. So this data set contains 12 classes: people, animals, house objects, and so on, similar to Pascal you know, segmentation data set, which is on real images. We gathered around 5,600 images of 4 different types of art movements: realism, impressionism, post-impressionism, impressionism, and expressionism, because as I told you, you can't actually look at artistic images as one domain. So we were trying to take some diverse art movements in order to train the network. And we also gathered a small set, which are around 600 fully annotated test images from the same art movements. Lastly, we also added an additional 135 test images from different art movements, not from the original one, so we can see the performance also on other art types or other domain types. So the overview of the method, as I said, includes 2 things. First of all, we train a separate network for each style, not for all of them together, because of the differences in style in each art movement. And the first one is we use image level augmentation, where we create what we call later pseudo images. And the second step is to create what we call domain confusion, where the learning network actually cannot recognize the difference, or in fact, it will use only features that are common to both the different domains, the photorealistic images and the art images. The first step, what we do is use you know, simple approach for style transfer. So we take Pascal images where you have the ground truth segmentation, and then we use ADA in order to stylize them to look like any one of the different styles that we gather. And this is what we call pseudo paintings, right? So these are pseudo paintings that then we can use later to train the networks, right? So we use these images where we have the ground truth because we started from photographs to train a simple segmentation network. But because we also want, in a sense, to confuse the network and use only features that are common from art and photographs, we use a very common trick, which we call domain confusion. And in that case, we use a discriminator. And we try to fool the discriminator so it won't recognize the difference between the real image, the real photographs and the art images. And then we constrain the segmentation network to use only features where you cannot distinguish between those two domains. And this allows us to train better the segmentation so that it will use only features from the art movements that are still usable also in the photographs. Putting it all together, it might look a little bit large, but the idea is that, as I said, we're training 4 different networks for each specific style. So we train a style transfer network, and then we create what I call pseudo paintings. We use them to run a supervised training approach for 4 different networks. And lastly, we do the domain confusion, where we continue to refine those networks in order to segment better the artistic paintings. Now, how do I use this approach if I have a new image? So one option is really to use the 4 different segmentation network and see which one works better. But in fact, first of all, the input could be not from these 4 specific artistic movements. And also, maybe there's a better way to combine the results of the different networks. And that's exactly what we did. So the main idea is we want to find a style representation for each new image that I need to segment. And what I do is we use a gram style descriptor, which was used previously in many other works, to recognize what type of style the image is. And then we compare it to the style descriptors of all our database, the DRAM database. Then we look at the k-nearest neighbors from the database of this new image, and using those k-nearest neighbors, or the number of k-nearest neighbors, we weigh the different results of the 4 networks to get the final prediction of our network. So in a sense, we found that this works much better than looking at each and every one separately. Now, first of all, this allows flexible prediction for unseen art movements as well, not just for the art movements that we were training on. And we got improvement of around 4 points over each specific one, over each specific segmentation network. So even if I take the maximum one separately, the combined one would be much better. But more surprisingly, we found out that even for the original training set, even for your original art movements, this type of inference actually helps improve the segmentation results for the original data sets more than the original segmentation network that were trained for these specific style. And we believe that this is because art movements are rather abstract, and in every painting you can find features that come from more than one movement. So using this type of combined approach helps you better segment everything. Again, in the quantitative sense, we were testing it on our test set. Of course, the test set does not include any artist that was used in the training set. And we found that our measure breaks the state of the art and is better. But as you can see, the results are still rather low. So there's still a lot of work to be done in this very, I would say, challenging domain of art. Some of the qualitative results you can see here. On the left is the images. On the next to it is the current state of the art on photorealistic, images, and then ours without this first step, ours with the second step, and lastly the ground truth. And as you've seen, ours got much better results, but there's still room for improvement. Here are some results on the unseen data sets. So these are images that, their feature or their artistic style is totally different than the ones that we trained on. And still you can see that we can get rather nice results. Some applications for our, for this specific segmentation is what we call comparative collection. So now we can extract and segment all the images of people, all the images of dogs, all the images of flowers from specific set of artistic movements, and then compare them or use them, to combine in other places. Another application is we call semantic guided style transfer. And in this case, we take both the input image photo and the input photograph, and we segment both of them. And then we use style transfer only on similar segmented classes. So in this example, you can segment a dog. And now when you style transfer from this specific image, you can see that the dog is much more coherent with the painting of the image compared to a method that doesn't use this type of approach. Similarly, here you can see the horse, right? So you have an image of a brown horse and a photograph of a white horse. If you just use style transfer without semantic knowledge, you get a white horse. And if you do, you get brown horses. Okay, so let's talk a little bit more about style transfer. And this has been a wave in previous years. There have been many works for transferring style from paintings to photographs. And in this example, I'm showing you two different stylization based on two different artists. And obviously, when you look at it, it's difficult to recognize which artists they are. I'm also going to tell you which artists. So one is Amedeo Modigliani, the other is Margaret Keane. And still, if you know the artist, it's difficult to recognize the differences between the styles. But how about now? If I show you this results, I'm sure that people would be able to recognize much better which stylization artist was used in each image. Because as we believe, stylization doesn't include only color and texture, but also geometry. And as you can see, Modigliani has very long faces. Margaret Keane has very round and big eyes. And so this is part of their style. So the difference between the domains of artistic paintings and photographs is not just color, texture, it's not just the content, but it's really also some severe geometric differences. So the motivation in this work was really to try and understand the geometric style in portraits. So you have many portraits, drawn throughout history, and many of them contain geometric style. And we first want to analyze this style, and then we want to synthesize new results based on this specific style. So how did we manage to do that? I've showed you already that facial landmark detection is a very common algorithms in computer vision today. Unfortunately, when you look at results of previous work on artistic images, as I showed you before, you get serious artifacts and they don't work well. So again, the idea was to look at the differences between natural faces and photographs and try to merge the differences and see and bridge the gap between those differences. And again, as I told you, there are large texture variation between portraits that are drawn or painted and portraits that are, taken from a camera. But there's also changes in the geometry of the human face. So when you think about the geometry of the human face, you can think of typical features, the shapes, the size, the proportions, the locations, and most humans have similar proportions. Obviously, there is variation, but not as large as you find in artistic portraits, where everything has much larger variation. So in a sense, we were trying again to bridge the gap using augmentation. The first augmentation is using stylistic augmentation of texture. And we start with a given image of a data set where you have the ground truth landmark detected. And we stylize it, in this case, using the Gettys algorithm and using different types of input artists. and you get different pseudo paintings again. However, this doesn't account for geometry. So what we also did is we did geometric augmentation. We found the different features in the face, and then we used some affine transformation to change the actual faces, as you can see here. And this changes the relative location, the aspect ratio, the scale, and so on. What we get something that doesn't look quite well as paintings or as art, but it does help when you use it for training neural networks. So the idea is to use this augmented data set and train a facial landmark neural network that, first of all, estimates the position of each of the different landmarks, and then refines it based on these positions to find the actual landmark on artistic images. Here you can see an example before we were training and refining the network for artistic images, and after. And after. Okay, so obviously both the geometric and the texture augmentation allowed us to create a much better accuracy and find exactly where everything is. Now, when you look at it in terms of the quantitative error, this is the cumulative error distribution. We were comparing our algorithms to various other face landmark detection algorithms. And obviously ours is at the top, it's the red one. But when you look at the graph, you say, actually, there's not much difference. Everything works more or less quite well. And this is true, only that, as they say, God is in the details, right? So the landmark detection algorithms work quite well in many cases also on art, but they're not very accurate. And here you can see the example on the left of a regular, not refined algorithm versus our algorithm. And you can see that our position of the landmarks are much better located according to the specific style. So how do we really see this? What makes the difference of this specific style? So what we were trying to do, is, as I told you before, is learn the geometric style. And looking at the human faces, if we detect the position of those landmarks, we can then gather each landmark together and create a sort of distribution with the mean position of each landmark and a variance ellipse around it. And as you can see, human faces are rather regular, and there's a specific shape that most human faces look like. But then we do the same also for our data set of artists. And what we found is huge differences between the different artists. So here you can see various artists or styles of representations of portraits. And I'm going to give you some examples. So here, for example, a Japanese artist, Utagawa Kunisada, you can clearly see the Japanese style eyes and the Japanese longer faces. When you move to Margaret Keane, for example, you can see the large eyes and the squashed face, because that's the style of her paintings. And the nice thing is, when you think about Pablo Picasso, well, Pablo Picasso has a huge variation. So, you see that the variance is huge according to or compared to various other different styles. So this is because Pablo Picasso is really all over the place. Now, another nice application is, now that we can find the correct detection of the landmarks for a specific artist, we can then average the different portraits of a specific artist and create the average portrait. Now, on the right, you can see the results if we just superimpose one on top of the other without any alignment. But because we now have the features, we can then align the features, and what we get is the average portrait of, for example, Modigliani. And here you can see another few examples of average portraits created for various artists. And yet again, you can see clearly that style is not only related to texture or color, but also to the geometry that specific artists convey faces. Lastly, I'm going to show you the geometry-aware style transfer. So in this case, you take an original image, as I've shown you before, a photograph, and then you stylize it not only based on the color and texture, but also based on the geometry. So what we do is, since we have a model for each different artist, we can sample the geometry of that specific artist and then change the position of the landmarks so that it will resemble more the distribution of that specific artist, and only then use the texture style transfer to actually create something that looks like the image. And here are some results. This is just texture, and as you can see, it's nice, but it doesn't really convey the geometric style. And here is just the geometric style. And lastly, the third row is combining them together. So when you combine both texture and geometric style, you can get much better representation for each style of different artists. And obviously we can also combine, right? So now we have a model for each specific artist. We can create new artists, which are in a sense a combination of the different artists. Lastly, I'm going to talk a little bit about more abstract representations, which are abstract sketches. And in this case, we were trying to synthesize or try to teach the computer how to synthesize abstractions of specific objects. So this work is called Clipasso, in a sense, because of the motivation image from Picasso. And the idea is that you take an input object or an image of an input object, and you allow it to create abstraction of that object using key visual features. Now, when you think about abstraction of sketches, you have sort of a whole range of specific abstractions. And we call the first one more geometric abstractions, where for example, you can use edge detection, and this more resembles the image, the specific image of a cat in this case. Or on the other hand, you have a more abstract representation or semantic representation that will resemble any cat as a semantic representation. What we're trying to do is really to take this approach and move it more towards the semantic approach. Now, one way to do this is to use sketch dataset, and there are many different sketches dataset that people have been collecting and using in order to create these types of sketches. But unfortunately, first of all, these sketches have each one different characteristics and only talk about specific style and abstraction level. So they can create various abstraction level. Our approach tries to directly rely on, not directly rely on sketch database, and try to learn the semantics using the correct representation. And in our case, we were first of all representing sketches using different shapes or different strokes. In our case, Bezier strokes. And the level of abstraction is guided by the number of strokes. The second thing is we were using optimization in order to rasterize or optimize the stroke positioning. And lastly, we were using as the loss function a clip-based loss. Now, because of lack of time, I'm going to describe a little bit just what clip is. So clip, in fact, is a neural network that was trained in a shared latent space of both images and text. And it is very good in extracting semantics from images, and it can be used for various applications. In our case, we were using only the image encoder, and we were basically trying to minimize the loss difference between the sketch that was optimized and the clip loss in two different representations. So I'm going to try and skip some of these because of the lack of time. but the idea is really to optimize based on two losses of clip. The first we call geometric loss, which uses the shallow layers, and the next is really the more deeper levels that define the semantics. And here you can see the optimization process. You start with a specific number of edges, and then this allows you to create various different representations that are abstract for a specific object. We also tried it in the wild, so everyone likes cats. So here's an example of 100 cats, random cats taken from the internet with their representation using our method. Okay, so to summarize, I hope I showed you that non-photorealistic images domain are still very challenging for both vision and graphics tasks. And even if we think about today's very strong neural network algorithms. The main reason is really the domain differences, and they include the subject differences, the color differences, texture, geometry, abstraction, and variation. So all these create these challenges for artistic or non-photorealistic domains. And we presented several novel methods for increasing domain differences. So first of all, on animation sequences, on paintings, on artistic paintings, and lastly, also for abstract sketches as well. So the main take-home message, I think, is really that learning and utilizing the right representation is really the key to try and move from photorealistic to non-photorealistic content and images. So thank you very much, and I'll be happy to take any questions if you have one.
Yeah, thank you very much. It's very interesting talk, and you talk about a few like really cool projects. Yeah, so if you have any questions, then please leave the message. So we're a bit run over time, but I do have a few questions. One is about the last work you talk about, like the feature from the sketches. So did you use a backbone network to extract the image level feature on that?
So as I said, what we do is we run both the sketch and the image through CLIP, which is a pre-trained network from OpenAI that is very good at semantic understanding. So we were certainly using this, but and then comparing the outputs or the middle layers of these two things. So we were not training in this algorithm. We were just using this, as you say, as a backbone for extracting the difference between the sketch and the image.
I see. Yeah. So yeah, I have another like more high-level question here. So you mentioned like there are two principles when you deal with like when you try to bridge the gap between the non-photorealistic set and realistic set. Is one is the like domain confusion, and I guess that is more related to like the feature you want to learn. Another thing you talk about the augmentation, like you try to like do some dataset efforts. So did you have like based on your observation, like do you have any comments on like which part plays the like more central role for your problem, and like what is like a more promising direction to explore next? I mean, which technology would like explore next?
It's difficult. I think it's really related to the task that you want to solve. I think for certain, I think augmentation, meaning trying to transfer the data that you have to be more similar to the data that you're looking at. This is one of the most, it's probably many times very simple to do. And so I think that's sort of a no-brainer. You should always try to use augmentation. The more interesting thing here is that geometric augmentations are not that easy to do. So style augmentation is certainly a very useful mechanism. Geometric augmentation is a little bit more difficult. Now, in terms of domain confusion and other types of method, these sort of give us the edge. So you can only go so far using augmentation, but domain confusion, for example, in this case, helped us a lot to actually further improve the results. So it's very difficult to say, I would say certainly both. So there's no one direction.
Cool, I see, yeah. So my last question is about the first work you talk about, the one working with the the cartoonish type of input. So do you think that like, because the cartoon is usually for kids, right? Like at least like most of the time it's for kids. So sometimes it's got a very like,
you see, Lindy that doesn't agree. She thinks it's also for adults. I also agree.
No, also for me.
Actually, I watch cartoon a lot.
Especially if you come from Japan. Yeah, in Japan.
Oh, right.
Yeah,
But,
they read comics all the time.
Yeah, but my point is, so usually for cartoons, there will be like some low-level features that makes the character different, right? You see, like the color can be very different, or the shape can be very different. So for maybe one character, it's like the face is round, and for another character, the face is square. So do you think like utilizing some like low-level feature here would also benefit the method?
Well, so I mean, as you saw, our method doesn't actually look at specific low-level features. What it tries to do is it tries to group together examples that look, that come from the same character. And then the network actually learns what type of features it needs in order to represent that specific character. In fact, I'm not sure that, in some characters, it's the color that is more important. In other characters, it's the shape that it's more important, and so on. So in fact, I think that what we described is really, a better approach, because we don't tell the network in advance what to look for, but we let the data sort of lead us. And the network finds the correct features. It could be texture, it could be color, it could be shape, it could be others. So certainly, and just answering your question, I think that it does use some low-level features for sure, but it can also use other features. So I wouldn't want to commit.
Like you mean your network will like explicitly like learn these low-level features instead of like providing them
looking at those low-level features. Yes.
I see. Cool. Yeah. Thank you very much for the talk and discussion.
Thank you, everyone.
Oh, actually, there are some questions in the chat.
Yeah. Actually, we have questions coming from our audience. So maybe given the time left, let's do one. Okay. Yeah.
Okay, I have a question.
And one from India. So do you think that it is possible to have computer appreciate art? Like distinguish from the good art from poor art.
Yeah. So I have to answer the question with a question. Do you think that people can, all people can really distinguish between high-level art, masterpieces, and just, poor artwork like doodles? So it's a serious question, especially today, because of, what is art, what is defined as high art, and what is defined as just, scratch. This is very difficult, but that's the answer for this specific thing. But I have to say one more comment. If you ask me any question, will computer do X? I personally believe that the answer is yes, eventually. Yeah, I mean, I actually believe that artificial intelligence is possible, maybe in the future. I don't know when, but I actually believe. So if people can do it, if you believe that people can do it, then yes, computers would be able to do it. Now, I also have another question about Clipasso. So someone asked me if Clipasso will work on cartoon Japanese style. So again, Clipasso works well on objects, but it doesn't really matter if this object is a photograph or a painting. So actually, it works well also on paintings, on structures, on sculptures, and so on. Okay, one more from YouTube. It's funny that artist images are already meant to be readily interpretable by human without retraining human vision. Does this reveal some fundamental limits of current vision algorithms? Actually, that's exactly my point. I think that vision algorithms tend to concentrate on photorealistic inputs, and human perception actually is better for sure than computers, but it's actually very good in non-photorealistic content. And if you want to push computers to basically have the same capacity as humans, I think that this type of research actually helps a lot, because then it allows computers to be more like humans, in a sense, to have abstract understanding, to have understanding of art, and so on. Okay, So I think that's.
I have a question.
Sure.
Yeah, very nice talk. So currently, if I didn't miss anything, you only focus on like a single image synthesis. So if
Yes.
I want to like generate a video with the style, do you think like the current algorithms can be easily extended to that? And
Sorry, create what? So a single image
video
as opposed to a video, yes.
Yeah,
okay.
and can be easily extended to video generation. And also, like, what do you think maybe the key problem or difficulties in this problem?
Yeah, so I think almost all algorithms, when you move from images to video, the problem is temporal coherency, right? So the problem is how do you, so you can't, apply an image-based algorithm frame by frame and expect that everything would look okay. So I certainly think that many of the algorithms I've shown, and I also have some work, a little bit work on video processing as well. But certainly they can be extended to videos. Maybe someone is working on it already. But in general, I think that the key point here is really the temporal coherency. So many times each frame could look very well, but once you play the video, you see jitter motion, you see something that doesn't fit. And so basically that's the point, temporal coherency, because it's a video. So that's the first. The second thing is more obvious. It's huge. Video is much larger. So if you want to apply something to videos, you need a lot of memory, you need a lot of power, of processing power, and so on. So that's the second challenge, I would say, for addressing video.
I also feel like probably the lack of ground truth can be another issue. Like if you just want to transfer it to some like cartoon style, that is possible, like for human to compare. Right? But if you want to transfer to like Picasso style, like Picasso never draw a sequence of images continuously, so it'll be difficult for like human to judge whether it's realistic or whether it makes sense.
But it's correct in a sense, yes. But there's a very nice movie called I Love Vincent, right? I don't know if any of you saw it, but it's a full movie that's created by Vincent Picasso style, which was hand drawn. So every frame was hand drawn by artists. I believe that we're very close to creating such movies automatically. So
yeah, that would be cool.
Yeah, that may be the ending note. So you also have a lot to show. So let's not take more of time.
Cool. Yeah. Let's thank Professor Ariel Shamir again.